let's say you have positive 2 microcoulombs. Imagine you have a rectangle like this, and then 3 of its vertices are have charges there. Okay, so I can ask question. For example, I can say, what is the total force on the positive 6 microcoulomb charge? So in other words, I want to find the total force on this charge due to those two, right? The total force on that charge. What is the total force on the 6 microcoulomb charge? B, I can say, what is the total electric field created at the bottom right corner? So what is the total electrical field created here? Right here. So notice I can ask what is the total field at an empty space, but I can't say what's the total force at the bottom right corner. So I need a charge there to ask the question, what's the total force there? I can't ask what's the total force there due to these 3, but I could say, what's the total electrical field created here by these 3, right? So that's kind of what this is asking, total electrical field. But you can't ask force here, okay? But in question A, I'm asking what is the total electric force, right, on this guy? Now, can I ask this question? Can I say what is the total electrical field at this corner created by these 2? Let's say, even before asking this, let's call it A prime. Can I say, what is the total electric field created at top corner, top right corner? Can I say, what's the total electrical field created here? The answer is yes, you can. Because the reason that these guys exert a force on that charge is they actually create an electric field right there. And then that electrical field gets noticed by that charge. Remember the idea of the tree again. These 2 charges create an electrical field here, and then this charge picks up on that, and then that's why there is a force. So if we want, we could actually find the total electrical field created here by these 2 charges, and then afterwards multiply that by the charge of that 3rd charge. Then we'll have force, you see? So tomorrow, the lab that we're going to do is we can mimic the simulation that we're going to use is FED Colorado. And the FED Colorado has one simulation that's really good. It can mimic this kind of situation. And we can actually do problems with this simulation, charges and fields. I can take this. So I'm gonna create that situation here. Let's see here. Grid. So I'm gonna go like this. See, that's the electrical field created by that positive. So I have 2 nanocoulombs. I could take 2 of them and put it right there. So right now I have 2 nanocoulombs. So each of this is a nanocoulomb. And then I have -4 nanocoulomb. One, 2, 3, and then 4. So then I get my measuring tape. So let's put this down a little bit. Hold on. Let's use right there. That's 150 cent. Yeah. Let's make it easier. Let's just go like this. 1. So that's a meter right there. One meter, 100 centimeters. So I have now -4 nanocoulomb. I'm going to change this to nanocoulomb, and this is a meter. And then this is 2 nanocoulomb. And I'm going to make this 6 nanocoulomb. Okay, so now I'm going to do this 2 meters.
Is that -40, Professor?
4 nanocoulomb.
Oh, -4 nano.
Yeah, because what I did to simulate it there is I put four of these nanocoulomb right here, and then I put 2 of this over there. So now 2 meters to the right of this. 2 meters is going to take me right there. Yeah, so now I'm going to put 6 nanocoulombs.
Will we be using this for our lab?
Yeah, this is tomorrow's lab. We're going to be using this, yep. And you could do problems with this too. So this could be kind of a homework help. So 1, 2, 3, 4, 5, then 6. So the cool thing is it shows you what the total electrical field looks like of these 3 charge distributions. See, electrical fields come out of the positive and they go into the negative. You see, they feed into the negative. So this is called a source of electrical field, and the negative charges are called a sink. So it's kind of like having a water fountain, right? These 2 are water fountains, and this is a drainage. Drainage is where the water flows into. So if you had 2 water fountains and 1 drainage, the water would flow like this, and then it feeds into this. But some of the water goes and just gets lost. It's not going to come back and drain into here, you see. So the water that is near here will drain into the drainage. You see, it goes like this and then it goes into here. So now we could also get the sensor. No, that's for voltage. We'll do that voltage later. Oh, let's get this sensor. This sensor, wherever you put it, will tell you the electric field at that point. Oh, it's so big. Values. Okay, yeah, so the electrical field here is 9 volts per meter, which is same thing as saying 9 newtons per coulomb. So if I want to know the electrical field right there, at the center there, let's see, yeah, it's not, it's disappearing. It should give me something. Oh, I see. So it should tell me the electrical field created right there. Yeah, maybe the app, the simulation is not built to give me the electrical field inside of a charge. So it's kind of blowing up. But over here, it should tell me the electrical field right there at the bottom right corner. Because the app doesn't give you force between charges. It only gives you the electrical field created at a location. So we can answer question B first. What is the electrical field on the bottom right corner? Right here. So according to this simulation, the electrical field is 55.1 at the bottom right corner. And it's at an angle of 95.7. Negative 95.7. So in other words, where's that measured from? Negative 95. Well, it's measured from the right side, right? This way, negative 95. It's measured from the x-axis. Okay, so according to that, the electrical field here would be this way, 55.1. Okay, so 55.1 newtons per coulomb, which is the same thing as saying volts per meter. Okay, so, and then this angle is 95.1. It's giving you negative 95.1. So let's see if we can get that answer. That's question B. What is the total electrical field created at the bottom right corner? Okay, so then what do we use here? Well, what's the electrical field of the, let's label these charges, charge 1, charge 2, and charge 3. So what's the electrical field of this charge at that location? So if it's a negative, it's going to create a electric field towards it, right? Since it's a sink. That's E1, right? This guy is a positive. It creates an electrical field away from it. So that's E2, right? Oh, no, E3, I should say. So I'm going to write that here bigger. So I have E1, E3 at that location is away from it, right there. And then what's E2? If you draw a line like that, right? So then it's positive. That means it's radially away from, right? Like that. It's like this, right? Then we'll call that E2. So now if you add these three vectors, it should give you the answer that they got. So that's why it's good, because you can check your work with the app. So how would we add these? Well, we can just solve what E1 is. What is E1? When you find E, since we already took care of the direction of E by saying it's to the left, you shouldn't put the negative again when you're calculating the E. Q1 over R squared. Remember, the electric field of a point charge was just KQ over R squared. The Q, I'm just going to put the absolute value of this charge, not the negative, right? So all I care about is the absolute value right now. So 9 times 10 to the 9th. And then the Q is what? 4 times 10 to the minus 9. Since remember, nano is 10 to the minus 9. And then what's the distance between these two charges? 2 meters, right? So then divided by 2 squared. Well, that's easy to calculate. The 10 to the minus 9 cancels the 10 to the 9th. That's why the simulation uses a nanocoulomb, because then it's just easy. It cancels with the K value. So what do you get here? The 4 over the 4 cancels out, and you just get 9. Okay, so the value of this vector is just simply 9. And that's newtons per coulomb. Okay, then we can calculate E3, which is just 9 times 10 to the 9th. And then the charge of that is 6 divided by the distance, which is 1 squared. That cancels, and then you get 54. So this vector is, oh, it's so much bigger than that. So it's like really huge. 54. Right, and then what's E2 gonna be? Okay, let's figure out this distance. If this is 2, right? So that distance is going to be what? Square root of 5, right? 2 squared, 4 plus 1, 5, square root of 5. So then the vector E2 is going to be what? 9 times 10 to the 9th times the charge of that, which is 2. All right, and then what else? Divided by the distance squared, right? So if the distance is square root of 5, then you're squaring that, right? Because remember, the equation is KQ over R squared. So if the R has a radical in there, you have to then square that, then the radical disappears. So then this and this cancels. So you have 9 times 2, which is 18, over square root of 5 squared, that's just 5. So the vector is what? 3 and 3/5, so 3.6. Okay, so now, how do you add these vectors? Well, this vector is already in the x direction. This vector is already just purely in the y direction. But a vector that has 2 components, we have to break those components up, right? So we have to break it into this component and then this component. We have to break E2 into 2 components, this guy and then this guy, right? So if this vector is 3.6, what would that component be? And then what would the y component be? Well, what's this angle? In other words, what's this angle here? That would be the same as this angle, right? Theta. Sometimes we don't necessarily need to find out the angle, but we just need to be able to say what's the cosine of that angle. You see, So in other words, E2x, the x component of this, which is this guy, right, is going to be E2 cosine theta, which is this angle right here. But then that's the same as this theta, you see. So this theta right here is the same as that theta. So then E2 is going to be 3.6, right? And then cosine of that angle is going to be what? 2 over square root of 5. You see? So we don't need to necessarily know what the theta is, as long as we can get the cosine of the angle, which is 2 over root 5. That's it. So that's going to be E2x. And then the y component is going to be E2 sine theta, and it's down, right? So then what is that going to be? 3.6. And then the sine of the angle is going to be what? 1 over root 5, right? 1 divided by root 5. 3.6 divided by 5 radical 1.60996. Okay, now I've broken that vector up into x and y component. Okay. So now I can combine the x component of that to the x component of this, because this is only in the x, right? So this is actually should be drawn a little bit bigger. So then the x component of that was what? 3.219, right? And then this one is technically, this is in the left direction, so it's -9, right? So then we add -9 to 3.219. In other words, this vector is bigger than this one. You see? So then we say E total x is going to be -9 plus 3.2199. -5.7801. E total x. Okay, what's going to be E total y? So then the E total y, both of the y components are negative. So I could just take them and add them and then put the negative at the end. Right, so I add 54 to this guy. Right, so the y component of that was 1.60996 added to 54. Well, that's just simply 55, right? So it's 55 point what? 60996. But then add a negative to that. Right? So you see with the signs, does anyone have questions with the positives and the negatives? I want to make sure you're following with that. The x component is positive, and then this one to the right, then it's the negative. When they're in opposite direction, that's when you have to be more careful. Then you have to say, oh, okay, this guy beats that guy. But then if they're in the same direction, you just take them, you just simply add the 54 and the 1.6. Okay, that tells you the X component of the total electrical field at that location. And this gives you the Y component of the total electrical field. Now, if I want to take the magnitude of the total electrical field, what do I do? The magnitude of the total electrical field, you do this squared plus this squared square root, right? Square root of the X component squared plus the Y component squared. Okay, so we're gonna square this guy plus square the 55.60996, square that equals, then square root the whole thing. 55.91. Total electrical field 55.91 Newton per meter. Are we close to what the simulation gave us? No, the simulation gave us slightly different, 55.1. Let's see here. It probably depends where I put this sensor, huh? Yeah, I think if I put it here, oh, right there, 55.9. Oh, wow. It's very sensitive to where I put it. Right? I have to put them in the right place. So 55.9. The angle, it says 96.9 now. It's slightly different. Okay, so now how do we calculate the angle? So for the angle, we say tangent of alpha is electric field in the Y over electric field in the X. So we take this number divided by this guy, and then take the tan inverse of that, negative 55.60996 divided by negative 5.7801, and take the tan inverse of that. So 55.60996 divided by 5.7801, tangent inverse, 84 degrees, right? But that's giving us in the first quadrant. It's giving you this angle, 84.06. But our vector, since it's negative, negative and negative, the vector E is in the third quadrant, right? So we add 84, we add 180, 264. Oh yeah, 264. It gives us this angle, right? So in other words, this angle would have been 84. Then we add 180 to that, and it gives you the 264. But the app gives you this angle from the 360, right? So then we can subtract this minus 360. There you go. Then take the positive of it. Or actually, you could take the negative of it. Yeah, because it gives you a negative. So it tells you negative 5.9. So this angle, it's giving you that angle in the simulation. Okay, so alpha we can say is negative 95.9 degrees. Okay, let's see here. Oh, it's giving you 96.9, so it's slightly different, 1 degree off. But we're very close. Okay. Oh, now you see it? Okay. So you get 2, -4. So this guy, this -4 attracts this charge. Then this one repels this. So then you do KQ1, Q2 over R squared. So then you take the product of the charges. So then you have 9 times 2. So I'm trying to find the force of this on that. So 9 times 2, 18. 6 divided by 4. And so that's going to be 2 goes into here twice, 2 goes into here 9 times, 2 goes into 6 3 times, 9 times 3, 27, and then 10 to the minus 9 nanonewtons. So 9 times 3, 27, and then 10 to the minus 9 is a nano. So this guy exerts 27 nanonewtons of force on this guy. And now I'm going to find the force of this one on there. F1, 9 times 10 to the 9th, times 4 times 10 to the minus 9, times 6 times 10 to the negative 9, over that distance squared. So this is 1 square root of 5. Right? So then that distance is going to be square root of 5 squared. So that just gives you 5. Right? So, and then now that one, the 10 to the negative 9 cancels this. 9 times 4, 36, times 6 over 5. So 36 times 6 divided by 5. 43.2 nanonewtons. This is giving us the nanonewtons. Then what do we do? Well, F2 is already in the extraction. So then we just break this up into X and Y direction. Right? So there we say F1x is going to be F1 cosine theta. This is theta. So then that's going to be 43.2 nanonewtons times cosine is going to be 2 over root 5. So remember, we don't need to know the theta, just the cosine of it. 2 over root 5. So times 2 divided by 5 root 38.639. Okay, now I'm going to put this as a negative because remember, when the forces are in opposite direction, we have to be careful. So then we're going to add the negative to the positive, and they're sort of going to cancel each other. And then the F1y is F1 sine theta. Then we have here 43.2 nanonewtons times sine of theta is 1 over root 5. 43.2 divided by 5 root negative 19.319. nanonewtons. And that's down. So it's by itself. We don't need to add it to anything. Okay? Just by itself. Okay, so then the total F total X is equal to this one we combine with that one, right? Because this is F1, it's just F1 is purely in the, or hold on, 27. Oh, no, sorry. F2 is in the X direction, that's this one. 27, that's this guy. And F1 was the magnitude of this. Okay, so now I'm going to combine 27 to the negative 38, right? So 27 nanonewtons minus 38.639 nanonewtons. Okay, and then F total Y is just simply going to be just this, negative 19, because that's the only force. The only force in the Y direction is that. So negative 19.319 nanonewtons. Okay, what's the total force then? Square root of 19.319 squared plus 11.639 squared. Okay, squared plus 19.319 squared equals, then square root of that, 22.554 nanonewton. Okay. And then what would its angle be? The angle of that force. Tangent inverse of this guy over that guy, right? Tangent inverse of 19.319 over 11.639. So remember the force, the total force is going to be the vector sum of this and this. So this one is going to be like this, something like this. That's the total force. Its X component is negative and its Y component is negative. So the probably, yeah, we could give this angle or we could give this angle. So I'm going to do 19.319 divided by 11.639 tangent inverse 58.93 plus 180, which is going to give us, this is 58, so plus 180. So that's going to give us 238.93. Or if we wanted to do it the way that they did it, they would give this guy, right? So from the 360, so we could subtract minus 360. 238 minus 360, negative 121.067 degrees. So 238.93 degrees or negative 121 degrees, and the total force felt by that third charge in the corner is 22.554. Now, even though the app can't give us that force, how do you think what can we do to the app to check our answer if we are correct or not? What can I do? Let's see who's clever here. What can I do to check that answer? Because if I put my sensor there, it's not giving me the electrical field there, right?
The bottom left one to the other side.
Okay, look what I'm gonna start doing. What am I doing?
Decreasing the charge.
Yeah, not just decreasing it, but completely taking it out. Now what could I do? Let's see, what was 2 meters, right? So that brings us here. So what is this giving me now? So I'm taking that charge on which I found the force, right? I'm completely taking that charge out of the picture. And now I'm asking, what's the electrical field of these 2 charges at that location? And it's giving me 120.6 degrees. Is that the answer we got? So is that the same as the answer that I got? I got 121.067. You see what I did? So I still was able to use the concept of the electric field to help my answer. You see, so what I did is I said, okay, go back to this, take that charge out. What's the electrical field of these 2 created there, right? And what's the electric field going to be? It's going to be the electrical force experienced by that charge divided by the charge of that charge, right? Of that charge on which we found the force. So how could I check my answer? So I found that the charge, the force on that charge was 22.554 nanonewtons. What's the charge of that charge at that location? What's the charge? 6 nanocoulombs, right? So then I can divide that charge out, 6 nanocoulombs. You see? So I can sort of go backwards. I can say, if I already know the force on the charge, then divide that force by the charge and find the electrical field at that location. So the electrical field is going to be what? The nanos are going to cancel. And what's 22? .759 newtons per coulomb. And what's the direction of that electrical field? Well, since the charge is positive, it's going to be the exact same direction as the force. So, which is this guy, negative 121.067. So just from knowing the force, we can go backwards and say, oh, the electrical field at that location, due to the first 2 charges, I expect it to be 3.759, and then go back and check it. Oops. And say, oh, 3.6. What am I getting? I'm getting 3.759, right? It's slightly off. 3.759, but that probably depends on where I put this, 3.759.